All right, so in 96, there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% per year after 1996. How many cell phone subscribers were in Centerville in 2008? So now you don't actually have to create an equation in order to answer this question, but the follow-up question calls for an equation. So you're kind of in a position where even though you don't really need to, it's probably in your best interest to. All right, so we go back to the exponential growth formula, which is n equals, well, it's really this formula. Oh, n equals, geez. Because, Common Core Algebra 1, they have to take notation that is traditionally used and change it for no apparent reason. It's this formula just with a plus sign. Right? So I'm kind of stealing my own thunder on exponential decay, because really the only difference between growth and decay is you have a plus sign instead of a minus sign, or vice versa. Right? So y equals the original amount, 285, times 1 plus, because we're increasing, 0.75 to the t power. All right. The cleaner version of that is 285 times 1.75 to the t. Oops, C daisies. Ultimately, we're looking for the amount of subscribers in 2008, which is how many years after 1996? 12. All right, so we're looking at y of 12, so 285 times 1.75 to the 12th power. All right. So you can handle this one of two ways. One way would be to type the equation in. You might question the need for doing this, but I'm still thinking ahead to part 2, or the second part. 1.75 raised to the t power, right? Well, we put x in the calculator. So not only is this not the traditionally used formula, it's in terms of t, but then in turn we have to put it in terms of x to use it in the calculator. So it's all over the place. All right. You can go to your table, scroll down to 12 if you want. Another way to handle it would be to use alpha trace y1 of 12. All right. The benefit of doing it this way, not really for this problem as much as it is for problems where the x value is some decimal, or maybe some really large value. This is a quick and easy way to get to the solution depending on what equation is in y1 without having to scroll through a table or use decimals or change your table settings. All right, so hit enter, and you get that number. All right, so they said don't consider a fraction of a person. All right, so we'll address that in a second. So this is approximately 235,126.427. All right, so then we just have to consider how many cell phone subscriptions we really have here. So we're going to say 235,126. All right. So that's for 2 reasons. I'll write subscribers. One, because it naturally rounds down. 5 or above, give it a shove, right? I forget what the other part of it is.
4 below.
Just say no, like something like that.
Sure.
Yeah.
Just
I don't know. I only remember the first part. So, like I before E except after C. I never remember what comes after that. I just remember that part. So anyway, based on the rounding, it would be this number. But even if this were 235,126.927, it would still go to 126. All right, because what happens is this little bit of instruction here: don't consider a fractional part of a person. Right, which means that unless you've gotten to a whole person, you can't assume a whole person. All right. So if this were a 0.9, we haven't gotten to the 127th person, so we can't just round up. You can't just say, Well, we pretty much have the 127th person. The way I kind of equate this to is a person goes into the AT&T store, they go to buy a phone and get a plan to go along with it. The like 0.927 would be like right before they signed the contract. They said, forget it, I'm not gonna do it. So did they actually get the plan? No.
No.
But they got like 92.7% of the way to getting the plan. They just didn't do the part that actually got them the plan. So we're actually not dealing with a percentage of a person or a fraction of a person. We're dealing with a percentage or a fraction of a subscription. Unless you have the whole subscription, you're not subscribed. All right? Like on YouTube. Did you hit the subscription icon? Well, you almost did, right? You hovered it over it. Your finger is like halfway to pressing on the mouse clicker or actually tapping on it. But right at the last second, you're like, no, I'm not going to do it. All right, so you're almost there. It didn't happen. All right, that's what's happening here. Now, the second part, how long will it take for there to be over a million cell phone subscribers? Now, you can go by the table approach, but that's dangerous. The idea here is that what we want to do is come up with the exact value and then use that to come up with an estimate. All right, so we need to get to 1 million. So 285 times 1.75 to the t power. We want to know when that's going to be equal to 1 million. All right, so the left side goes in as y1. The right side goes in as y2. And we use the solver. All right. So I already have it in y1. I'm typing in 1 million for y2. The benefit of using the solver again is I don't have to worry about the window. In order to come up with a good window, you kind of sort of have to have a sense of what the correct answer is. All right? If you have no sense of what the answer is, how do you come up with a window to then come up with the answer? All right? It's not a really good approach. Solver doesn't require you to know the window, or at least not for these kind of functions. So math, solver, I have it set up. Some calculators are set up differently, but since I know there's only going to be one intersection between a horizontal line and an exponential function, all I have to do is hit alpha and enter. So I get that number.
Mine says that the value exceeds my calculator.
Okay, I'll take a look in a second. So t is approximately 14.587. And that would be years. All right. So we just want to answer the question because they talked about how long will it take for there to be over 1 million cell phones. This is how long it would take to get exactly to 1 million cell phones. All right. So depending on what the rounding instructions are, we might say in the 15th year. You might say t is greater than 14.587 years. Anything that gets the idea that it's not particularly that number. Yeah, sure. Let me just. Or in the 15th year. So A is the initial amount. R is the rate of, well, it could be growth or decay. Growth or decay. And T is time.
In years. Or anything.
That's only for compound interest. Time determined by units in R. All right, so whatever units are used for the R value, related specifically to time, that's the units of time. So if it says it's increasing by 13% per day, then time is in days. All right, regardless of what everything else says in the problem, that's your key indicator. Now, I mentioned this last time that R is the rate of growth or decay. So if I'm writing the same stuff to define A, R, and T, what makes this any different? Well, really not much of anything, because the actual formula, it's really kind of misleading. It makes it seem like there's two unique formulas. But the real formula, and I'll just write it, oh, that is not my scrolly thingy. The real formula is y equals a times 1 plus r to the t. All right, so this new formula isn't really a new formula, because if r is positive, you're dealing with growth. If r is negative, it's decay. All right, so if I were to take that original formula from last class, 2 classes ago, whatever it was, and make r a negative number, I get this new formula. Right? So you're not memorizing a brand new formula, you're working off the same formula with a different type of r value. All right, so what that means for us, it's a good thing. It means that this isn't any more or less difficult than it was 2 classes ago, last class. Ben bought a new car for $15,000. As he drove it off the lot, his best friend Tony told him that the car's value just dropped by 15%, and that it would continue to depreciate 15% of its current value each year. If the car's value is now $12,750, according to Tony, write a function that models the value of Ben's car T years after driving it off the lot. All right, the old adage is that the car is actually worth 50% of its initial value the minute you drive it off the lot. That's kind of a standard rule of thumb, but I don't know that it's exactly 50% because some cars retain their value better than others. Like if you drive a, oh man, here I go, I'm going to offend somebody. You drive a Kia off the lot.
What's wrong with that?
You're probably looking at 50% of its original value at least. If you drive a Honda off the lot, it's probably closer to 30, maybe 25% of its initial value. All right. If you drive, no, those depreciate. It depends on how they're kept. If they're in mint condition, it's a different story. But like, no, like a high-end car.
Mercedes.
Yeah, Mercedes is closer to the 15%. Volkswagens do well. Volvos do well. Porsches do well. But then you start getting into like Maseratis; those don't do as well. You know, because yeah, exactly. That's really what it comes down to. Because if your alternator goes in a Honda, you don't have to call around to find one. But some other cars, that's the case. All right, anyway, very straightforward. Y is equal to 15,000. It depreciates at a rate of 15% per year, so 1 minus 0.15 to the t, or you might write y equals 15,000 times 0.85 to the t. It seems like I'm picking on Kia. It's because I am. Yeah, the Kia drivers are the worst drivers in the world.
My mom's a Kia driver.
Is she? One of the worst drivers in the world? No? She might be the exception.
She goes way too slow, though.
Ah.
Which is ironic because my grandfather actually goes really
Kia
slow.
driver? Subaru. There are personality profiles that are aligned with the kind of car that people drive. I have found that people who have Subarus, they think because of the safety record of the Subaru that they're somehow in like a protective shield, so that they can do whatever they want. It's going to be fine. It's a safe car. So drive it off a cliff, it'll be perfectly okay. No, it doesn't work that way. So value after 5 years.
That was so big. Sorry.
Yeah, Audi, Kia, and BMW drivers, the worst. Well, I mean, you can drive fast and still be relatively safe. Like, you don't have to like duck and weave in and out of traffic, cutting people off and things like that.
I saw someone with an orange but it was like popsicle orange, and I was like, that's sick.
And my claims are actually backed up by data because of my stat classes. I have students do projects, and they ran a study. They tested the safety of different cars. So now it's a smaller sample, but it's still a thing. So 15,000. Now I'm putting it in general form. So 0.85 to the t power, or in the calculator's case, x. And then I could go to the table this time, for example, because 5 is a nice value. Now just be careful. When you go to the table, that number in the y column is an approximation of the correct answer. You want to hit the right arrow to get on that number so you can see what the most exact form is. Now we're talking about dollars and cents here, so I'd probably want to go out to 2 decimal places. So this car is worth $6,655. And, well, as it turns out, oh no, actually it would be 58 cents, not 60 cents like the table would make us believe. All right. So the car started off brand new 15,000, so maybe we are talking about a Kia. All right, because like I'm just trying to think of like an economy car. Like even like the cheapest Honda Civic is more than 15 grand.
Yeah, it's like you did. It's like 19.
Yeah, you're closer to like 20. So, yeah, but this is telling us after 5 years, the car is worth $6,655.58. So now think of this in a real world context. Let's say you didn't have 15 grand on hand, so you have to take out a loan. All right, so you take out a loan in the amount of $15,000 in the beginning of 5 years. All right. It's very dissatisfying to know that at the end of those 5 years, when you've just paid the equivalent of like, I'd say $25,000 back, because you're getting charged interest. So you paid back the 15 grand plus interest. So let's say like $22,000 to $25,000. You paid all that money, and your car is only worth almost $6,700. All right, so cars depreciate. So if you're going to invest your money, you probably don't want to invest it in cars, unless you're Derek Jeter. All right, so because apparently he had an entire floor of his mansion that was converted into a garage, and that's where he has all of his collector cars, like 20 of them, I think. Yeah. But those are instances where the car's value is not depreciating it because he's not driving those cars through rush hour traffic. He's getting them shipped to his place, and then they're used as like, it's basically like a museum, right? So the follow-up question here, how can you tell just by looking at your function if the value of the car is decreasing? It's very simple. The R value, right, R value is negative. But more importantly, the base of the exponential is less than 1. All right. Before we started talking about word problems, when we were graphing, we came up with the idea that if the base of an exponential is more than 1, it's growth. If it's less than 1, it's some kind of decay. All right. But you could also take note, you look at a situation like this and you say, okay, I want to try to hang on to the car for a certain number of years, but I also want, like, let's say you want to hold on to it from 5 to 10 years, somewhere in that neighborhood, but you want to be able to get the most bang for your buck when you go to sell it, all right? So if that's going to happen, you might consider a function like this, but then you also have to consider the condition of the car, right? Because as time goes on, there's wear and tear. So not only is time a component that causes a decrease in the value of a car, but also scratches and actual just wear and tear on the mechanics of the car, like the engine or transmission or things like that. So as time goes on, the car ages, it's naturally worth less, but over time, the car itself loses value too. So it's kind of a tricky situation, and definitely something really challenging to manage.